in this lecture, I'm going to show you a beautiful application of the theory of species to the problem of counting the number of trees. So for that, I need to define the operation of pointing on a species. So let's get straight away to the definition. Let F be a species of structures then F dot is the species given by F dot of U is F of U cross U. So you give an F structure to U, but you also pick a point in the set U. And transport of structure is defined by if you have a bijection sigma from U to V, F dot of sigma. So now the argument will be firstly an F structure and secondly a point. And this is just F sigma S comma sigma U. The most obvious possible definition. So let's see how to visualize this. So suppose you have F structure. So you have a set U and you have an F dot structure. Let me then this is nothing but taking an F structure on that set, but also singling out one element of U. So to speak, you're pointing at this element. That's supposed to be a finger pointing, maybe a cufflink. Okay, so you're pointing at this one particular element of U. To give you a concrete example, a rooted tree is just a pointed tree. For example, if you just have some tree like this, and I point at one point, then I can take that point as the root and redraw the tree so that that is the root. So maybe I've been drawing roots as roots in red in the past, so I can think of this as a rooted tree, one child on this side. So this is a correspondence between pointed trees and rooted trees. So now let's look at a very simple proof of Cayley's theorem. Oh, but before that, let me tell you how to compute the various generating functions associated to the pointed species. So that's achieved by a very simple theorem, and the theorem says that F dot is equal to x times F prime. So let me again give you a proof without words of this theorem by just drawing a picture. So on the one hand, we have an F dot structure, so which means that we have an F structure, but we also point to a thing. I want to show that this is the same as an x dot F prime structure. So what I'll do is, let me just create some space over here. So I'll just extend this. And what I'll do is I'll take this point here and I will move it. Let's not remove the line though. I'll just take this point here and I'll move it into a separate part of the set. So I'm going to partition the set into two parts, and on the one I have an X structure and I'll replace this by the star. So now here I have an X structure and here I have an F prime structure. So this is X dot F prime and this is F dot. So F dot is X dot F prime. And so right away what we get is ZF dot is x1 del del x1 f of x1, sorry, ZF of x1, x2, x3 f dot tilde of x is x del del x1 ZF. Should probably write it like this. Can't simplify this much more here, but of course the nicest expression is for f dot of x, the exponential generating series. It's just x f prime of x, or if you wish, x times ddx of fx. Okay, so let's look at another example which will lead to the proof of Cayley's theorem. The species of vertebrates. So V is just defined to be A dot dot. You point twice. Why this strange name? Well, let's just look at a picture. So we'll take a tree without any root. And now I must point at it twice. So the first time I point, let's say I point at, well, let me just add one more. So let's say I point at this vertex first, and then the second time I point at this vertex. So I'll circle it twice to indicate that first I pointed here and then I pointed here. So you can now think of this as a head. The first point I will call a head, and the second point I will call a tail. And because this is a tree, there's a unique line, path actually joining the head and the tail. And that you can think of as the vertebral column. So this is the vertebral column. It has 1, 2, so on the one hand, a vertebrate is a tree pointed at 2 times. But on the other hand, a vertebrate is an L plus assembly of trees. Why is that? Well, what you can do is you can think of this vertebral column as an L structure, and each node of this vertebral column is in fact a tree. I can just make this clearer for you. Well, first let me just copy this out. And the trees here are, so here's one tree, here's another tree, here's another tree with just a root node, here's another tree with just no, that's and here's another tree. So this is an L plus assembly of rooted trees. Each of these trees is rooted. This vertex here is the root. This vertex here is the root of this tree. This vertex here is the root of this tree. And this vertex is the root of this tree. So let's put together these two things. And so firstly, what we get is that from this identity, what we get is that if we have f of x equals so the nth, let's just write it like this, f dot n cardinality is n times the cardinality of f of n. Of course, this is also obvious from the way we defined an f dot structure. You take an f structure, so you have so many, and then you point at one of the elements of u, so you have n choices for that. And so this first identity says, this says that the number of vertebrates on a set of size n is n squared times the number of tree structures on a set of size n. And the second identity says that the number of vertebrates on n is the same as the number of L plus A structures on n, but remember, L plus, the number of L plus structures on any set is the same as the number of permutations on that set. And so I can just, if I'm not saying that S is isomorphic to L, but S is equipotent to L. And so what I get is that this is S A n, but that is nothing but we've seen that S of A is endo functions. And then you ask, well, how many endo functions are there on a set of size n? It's n to the power n. So what we get is n to the power n is n squared times number of tree structures on a set of size n, which means that the number of tree structures on a set of size n is n to the power n minus 2, which is a famous theorem of Cayley. Of course, it's very easy to count the number of graph structures, or say simple graph structures on a set, because given any two vertices, either you put an edge or not. But it's of course much more subtle to count the number of tree structures on a set of size n. And this is a very simple and elegant proof, which you won't forget once you understand it, of Cayley's theorem. I should have been a little careful here. This step only works if n is greater than 0, because here we have L plus and here we have S. And this formula only holds for all n in P, all positive integers.